All right, so welcome back from spring break, everybody. This is going to be lecture 18. It's the first in what should be a four-lecture unit on star trackers. And we're going to see, first of all, we're going to talk about what star trackers are. And we're going to see how the whole concept of making a star tracker and the algorithms that are involved can be split up into four basic areas. And we're going to talk about each of those areas in their own lecture. And we're gonna try to coach you through homework four. Homework four is up right now. You can go read it if you want to. I've gotten explicit permission to post a slightly modified version of one of the Artemis 1 flight images. Like this is a picture that one of the cameras took on Artemis 1. It's on LMS. You can go download it. It's a 5 megabyte image. It's a TIFF image. And what you will be tasked to do is to perform star identification and ultimately tell me the attitude of the camera when it took that picture. So you're going to make a star tracker completely from scratch. And so that's going to be quite a steep hill to climb. So I definitely encourage you to work in groups of two or three or even four and break this up. This is going to be the first homework assignment and possibly the only one where I do not expect you to write every line of code that gets your star tracker running. If you want to partner with somebody and then split the tasks up, you can do a lot of the programming in parallel. Some of you can be working on the image processing and line of sight acquisition, while others of you are working on creating an invariant index. We'll talk about what that means. To the extent that you want to parallelize the work, I definitely encourage that. Um, so why don't we get started with the notes? So I'm going to share my screen. And there we are. So we're going to be talking about space cameras. So I'm going to start with a little exercise here. I already said space cameras here. So just imagine for a moment, we kind of had this discussion last lecture. You might remember last lecture was about inertial navigation. But just play with this for a minute in your mind. Imagine that you are an astronaut, and that might not be so hard to imagine after we just had our discussion about the astronaut application window being open now. Just imagine that you're in space, you've got your helmet on, you're floating around, and all of a sudden you realize that you're lost, right? Which is a dreadful thing to be lost in space. So, what do we do? There's got to be some way to get yourself unlost in space. And so, if you were lost while you were hiking, maybe you've got your compass and your map and you can kind of take a swing at trying to figure out where you are. If you're in space, what do you do? And this is not a rhetorical question. How do we get unlost in space?
I have a feeling I know where you're going with this, but you could look for constellations like the North Star or
Ah, okay, very good, very good.
Big
So
Dipper.
where I was imagining this would go, Corey, you actually even jumped over where I'm going with this. But that was exactly what I was going for. I was going to say if you're lost, you could look for the Earth because you're probably right next to it, unless you're really far away from the Earth. Depending on the nature of the mission, right? You could look for the Earth, you could look for the Moon, you could look for the Sun, you could look for the planets. You might be able to figure out where you are from that information. That's what I was imagining you would say. And then I would say, but Corey, how would you even know where to point your camera? Which way is your camera pointing right now? And so the point that I was going to arrive at is that knowledge of the attitude of your vehicle has to come first before you have knowledge of the position or the velocity of your vehicle, right? You don't know where to point your instruments, your science instruments or your navigation instruments until you know which way you're pointing to begin with. And that all starts with a star tracker. So star trackers, well, there are other instruments to determine your attitude, but star trackers are the gold standard, and they're on absolutely every spacecraft these days. They're pretty much ubiquitous. So I was going to say, you must know your attitude. Oh, my handwriting will have deteriorated in the week that we weren't working together. Sorry about that. You must know your attitude to find your position or your velocity. So attitude determination must come first. So there are several instruments to measure your attitude. but star trackers are the gold standard. So the Hubble Space Telescope used star trackers. Orion uses star trackers, right? Star trackers are, you'd be hard pressed to find a spacecraft that isn't using star trackers these days. You know, there's reasons why some vehicles might choose not to. The International Space Station actually does not use star trackers; they use something else. But star trackers nowadays are pretty much ubiquitous, and they are completely autonomous, right? They're autonomous, and you're measuring, you know, inertial space. You know, some of the other instruments for measuring your attitude will involve measuring the Earth, or they'll involve measuring the sun, or they'll involve measuring the Earth's magnetic field. It's like, great, but star trackers work everywhere, right? They work everywhere that there are stars. And if you're in space, hopefully you can see stars. So, how does a star tracker work? There are 4 steps. So, first of all, those of you who, I guess I probably should have started with, what are star trackers? Star trackers are a type of camera that takes pictures of stars. So, how does a star tracker work? And to your point earlier, Corey, you spoke up before, right? You take pictures of stars and you say, okay, great, now I have a picture of stars. How does that help? It's like, well, if you can recognize a constellation and you know which way the constellation is in some broader context, if you can describe the orientation of a constellation, say in the International Celestial Reference Frame, and you can see that constellation in your camera, that helps a lot. That helps a lot to tell you which way you're pointing. And so mathematically, we don't actually need to work with recognizable shapes. We can use what's called an asterism, or a group of stars of any size greater than 2. And you can recognize, quote unquote, recognize that asterism in an image, look it up in a database, determine where all those stars are in the night sky, and then determine your attitude. So there's going to be 4 steps to this, and I'm going to show off my drawing skills, so apologies in advance. But these are the 4 steps, and each of these corresponds to one of the next several lectures. So we'll begin with a camera. This is a camera. That's how I draw cameras. And it's going to be taking an image. Almost looks like a projector on a projector screen, but not quite. And there's going to be some stars in the distance. And you're going to be measuring those stars. So there's 1, and there's 2, and there's 3. That's not terrible. There we go. So the very first step is finding from an image, from a star field image, finding what are called line of sight, or LOS, directions to stars. So each of these, and I'm going to maybe color code this. No, I'm going to get away without color code on this one, but I'll need it for the next image. You can imagine that each of these is a unit vector from your camera to a star. So you're a quarter of the way done with your star tracker adventure if you can do image processing. We're going to talk about this today, image processing, to determine the line of sight direction from you to the star in your local reference frame, in a camera reference frame, essentially. That's step 1. Step 2, I guess we'll call this step 1, is operating a space camera. Step 2 is you need a map, specifically a star map. So let's say here's the Earth. Got some continents. There we go. Let's say that you've got a direction coming out of the Earth, and let's say that you've got a star up here. The direction to this star can be thought of as some azimuth angle and then some elevation angle. And you can imagine a whole, now this is not how it actually works, but you can imagine a whole dome with stars on it. Each star, you would want to know its azimuth and its elevation, right? And so this is going from reality to a line of sight direction. So you're going to meet in the middle, right? You're going from the image to a bunch of line of sight directions, but astronomers have already created star maps going from reality to a bunch of line of sight directions. So ultimately, we're going to be comparing not exactly line of sight directions, but something that you can compute from those. So the third step is an index search. So this is going to make more sense as we continue. I hope that we can refer back to these images as we start to feel more and more comfortable with star trackers, so it makes more sense. The third step is an index search. So what we're going to wind up doing is we're going to compare something called invariance and use that to ID stars. So our third lecture, we'll be talking about star identification. So we don't know what invariants are yet, but they are essentially a numerical name tag for a group of stars. And that's going to make more sense as time goes on. And you can imagine that your name tag, let's say it's a three-dimensional name tag. You've got some information in the x direction, some information in the y direction, some information in the z direction. Then your index of groups of stars becomes a point cloud. And let's say that you are searching this region of your index for any potential matches, and that region corresponds to this point, some dotted lines. You've got some point in 3D space, and you're saying, I think I see a group of stars that I recognize here. Let me look in the index to see if there actually is something that matches that description within some error, right? There's always going to be error in real life. And let's say that you've successfully identified the stars. You say, I've got it. Those stars in my image are these stars in real life. I know it. I'm absolutely sure. The final step is something called Waba's problem. We'll talk about who Waba is later. And that's the actual math of finding your attitude. So you've got basically a before picture of stars and an after picture of stars. And the only difference is the fact that you are facing some arbitrary direction. So in this case, you've got your camera and you've got some rotation going on. And you're trying to find what rotation causes these line of sight directions to line up with actual stars. Those are the 4 steps. Space camera, which we're going to talk about today, you go from an image of stars to a bunch of line of sight directions, which is actually much easier said than done. The second step is putting together a star map. Thankfully, astronomers have already done that for us, but we're going to talk about how star maps work and how us as navigators can use them. The third step is an index search so that we can actually identify the stars that we found in our image. And the fourth step is actually solving for your attitude transformation matrix or your quaternion to tell us which way our camera is facing. And those are the 4 steps. So these are, in case you're wondering, Lecture 18, Lecture 19, Lecture 20, and Lecture 21. And the eagle-eyed among you might have noticed that Lecture 21 is 1 day before this homework is due. So I'm almost certainly going to be granting a small extension on this because I want to give you a reasonable amount of time to get this done. This is where I wish I could just dump all the information today and then you could break this up and tackle this problem in parallel, but there's only one of me. And so I'm going to need to go through these things sequentially and in an order that hopefully makes sense. So I'm not extremely rigid about the deadline for this homework. I'll work with you, but it's important to me that every single one of you has a working Star Tracker script that you and 1 or 2 teammates wrote on your computer. Like every machine needs to be a Star Tracker in addition to whatever other stuff you use your computer for. So questions on that discussion? Otherwise, we're going to dive right into the space camera topic. All right, so far so good. So today, I would set my pen down and then forget which way I set it down. Today, we will focus on space cameras as navigation instruments. And here comes more of my sought after artwork here. So yeah, wish me luck. All right. So we've got a little box, and then we've got another little box. That's a camera. Can't you tell? And then we've got this. And then we've got some stars. All right, let me add some detail here. So these are meant to be lenses. That's what I'm going for here. And then this guy, which we will explain, is the focal plane array. And then that goes over into a separate box. There we go. And we're going to get some dotted lines going here. And I'm checking my note. I think that's it. That's your space camera. So let's start labeling things. So starting from the right, this is a star field, not to be confused with the video game star field, but an actual literal star field. And this is your camera. What you have here is, it's a little bit like a silencer on a gun. This is a light baffle. And it works the same way that if you've ever seen a racehorse and they wear these little hats with flaps on the side so that they're forced to look ahead, they don't get distracted. They're called blinders. The blinders on a racehorse is the same idea. You're blocking light that you don't want to land on the camera, right? So you don't want, let's say that you've got the sun over here shining its rays and just generally being a nuisance. The sun is great, but we don't want it in our star tracker. Like, I know the sun is a star, but we're not trying to track that type of star or trying to track stars in deep space. So given that, we would rather avoid any unwanted light entering the camera that we are not specifically going for. This angle right here, that is the kind of area subtended by the camera, is the FOV, or the field of view of the camera. And there's actually going to be a vertical and a horizontal field of view. So we'll have to keep that in mind. What we have in the middle here, this series of lenses, is called an optical assembly or lens assembly. Those are your lenses. So those of you that are photographers who have ever worked with cameras before, I remember the first time I bought a camera online, I was actually buying one specifically to put together a star tracker on a project that I was working on. I was trying to make a cheap star tracker out of Arduino parts, and or Raspberry Pi, I should say. And I bought the camera, and it came in the mail, and I was just I was dumbstruck. What's the word? I was flabbergasted to find that it didn't have a lens. I'm like, what the heck? Does it come with a lens? Is it even a real camera? It's like, well, real photographers will tell you that no, the lens is its own thing. The camera is actually this part right here, which I'm going to label focal plane array. So the focal plane array, and I'm going to write this all down, so you don't need to be taking notes on this. Just try to keep up with the drawing. The focal plane array is where the magic happens. That's where photons become electrons, become voltage charges, become voltage charges. And then those are read off into what's called a data processing unit. And that is where voltages become an image, right? So a digital image. And the optical assembly is for focusing the light. So I did not realize that you need to pay extra money for the lens, and that the lens can easily cost as much as all of your other stuff combined, which it's like, wow, okay. I was very humbled by that experience. But so that is a space camera. And I mean, what I'm drawing here is a digital camera, right? This is not specifically a space camera. Space cameras, like cameras that are rated for space, are kind of ruggedized, they're radiation hardened, they are built in such a way that they can withstand the vibration environment of launch. But for practical purposes, we're just talking about digital cameras here, essentially. So your phone does all this. Your phone doesn't have a light baffle, but it has an optical assembly, a focal plane array, and a data processing unit. You might find that your phone takes disappointing pictures of stars, and we'll talk about why that is. We'll talk about why some cameras are better suited for taking images of space than others are. But let's turn all the things that I just said into words on a page here. So a conventional space camera consists of going to try to scroll down. There we go. I got the image on there, and then you can see the notes. The first, starting from the right, is a light baffle, which blocks stray light. The second is an optical assembly or a lens assembly. And this is a series of refractive lenses which focuses the light. The light is directed onto a focal plane array, which is where the magic happens. So this converts photon counts into electric potential, electric charge, basically. And that uses something called the photoelectric effect. And we're not going to go into the physics of how that happens. You may be familiar, there are CCD or there are also CMOS focal plane arrays. We're not really going to go into those either. You could certainly go look that up on your own if you're interested. For now, we're going to treat this as a magical device which turns photons into electrons and leave it at that. But there's a ton of, I mean, you could teach an entire course just on this topic. So those of you that are curious, I definitely recommend you look into it further. And then finally, I'm going to scroll down just a little bit further. We've got a data processing unit, which converts voltages, a series of voltages into a matrix of numbers, because a digital image is just a matrix of numbers. You've just got an address, which is the number of pixels over and the number of pixels down, and then you've got a brightness, which is the number at that element in the matrix, which some of you might have guessed that already. Some of you might have background in image processing, or you might have experienced that before. Some of you might just be thinking about this for the first time. Hopefully it makes sense that the results, us being matrix math geeks to begin with, we are going to arrive at a matrix when we're done with our, image acquisition, essentially. And so ultimately we arrive at a matrix of numbers, one per pixel. And these numbers are limited by bit depth. So if you have a 8-bit camera, if you have a camera where each pixel has one 8-bit number or one byte of memory, well, a byte of memory goes between 0 and 255. So for example, often your digital image is going to be between 0 and 255, for example. So if you have a 5 megapixel camera and each pixel has one byte of information, then your image, assuming you don't do any compression, is going to be 5 megabytes. And that's what you're going to find with the image that you download for homework 4. It's going to be a 5 megabyte image because there's no compression on it. We don't like to do compression on Starfield images. It's not, it does not help things to go well. So questions on that, or are we feeling good? We can keep on moving. All right. So next we're going to talk about the geometry of which pixel a photon falls on. So you've got some star out here in space, and ultimately that becomes a number in a matrix. But which element in the matrix, or which pixel on the focal plane array? How does that happen? So we're going to talk about something called the pinhole camera model. The pinhole camera model. So a real camera contains multiple refractive lenses. It is often useful to model the camera as though its lens assembly shrunk to the size of a point, or a pinhole. That's where we get the pinhole camera model. And that's actually some of the most ancient cameras that we know about. So before cameras, it was understood that if you had, let's say, a tent and there was a bright scene outside and you poked a hole in the side of the tent, it could actually, if you got your focal distances and everything right, you could actually project an image that was upside down and backwards of the outside environment onto the opposite wall of the tent. And that was kind of that harnessing that idea is actually where some of the early camera development came from. But that's a known optical property that light tends to project itself that way. And so we'll one thing at a time, but the location on a digital camera of this fictitious point, which does not exist, right? This is a point that we are making up for the purpose of math, but it's somewhere inside the camera. The location of this fictitious pinhole is referred to as the focal point. The distance from the focal point to the focal plane is what else? It's the focal length. These are terms that might be familiar if you're familiar with photography and cameras. The image, which is projected, so the projected image at the focal plane is upside down and backwards. And must be rectified. And you might be thinking, oh, that's kind of weird. So when you focus light through a pinhole, you get an upside down and backwards image, which the computer just needs to know to flip around and put right side up again. That doesn't happen in nature. It's like, actually, it does. It's happening inside your head right now. So your pupil of your eye is essentially a pinhole. The light is projected onto the retina, onto the light sensitive cells at the back of your eye. Honestly, the human eye is a pretty decent, like, it's a lot of the same general design as what's going on with a camera, right? You've got uh, so instead of an optical assembly, you've got your pupil and you've got kind of the muscles that actually, control the shape of your eye. And then you've got at the back your light sensitive cells. And then all of that goes to a data processing unit. And it's theorized that the first brains that evolved, many millions and billions of years ago, were there to process light sensitive cells. That essentially image processing was where brains came from in the first place. Because you have plenty of animals like a starfish, for example, that can't see, that doesn't really need a brain. Its whole nervous system is distributed throughout its body. But it's hypothesized that brains came about to process light sensitive cells and signals from light sensitive cells. So you can thank this for your brain, basically, and all the problems it's caused you. And yeah, the image that is projected onto your eye that goes to your brain has to rectify it. Otherwise, it would look like everything was upside down and backwards, which I think is kind of neat. So here comes another drawing, and this is the pinhole camera model drawing here. So we're going to start with our pinhole right here. And I'm going to have over here a focal plane. And then I'm going to have over here another plane, which we're going to talk about in a minute, which we have not mentioned yet. And let's say that this is the same point in both images. And so we're going to dotted line, solid line, solid line. Okay, clearly we're going to try again. Don't you erase, but I'm going to erase because I was not pleased with my performance. There we go. That honestly still looks pretty bad. I want this. It's supposed to be the center of both. That's the point. There we go. And then that's going to continue forever. We've got another direction here and another direction here, starting to look like a coordinate system. And over here, we have what we're going to call the focal plane behind the focal point, and this distance is the focal length, which we're going to write as f. And then in front of the focal point, so to be clear, this is the focal point. In front of the focal point, some distance, which we're just going to call 1, is the image plane, which we are going to talk about, but it is a fictitious plane that does not really exist. Now we've got a coordinate system kind of baked in here. So this is actually the x direction. This is the y direction, and then this is the z direction. And you can use your right hand to confirm that that is a right-handed coordinate system. We've also got another coordinate system here, which is in the image plane, where this is the u direction, and then this is the v direction. Okay. And let's say that we've got some point out here in space that looks like a star, and that star projects to this point here. So it looks like this. And then I'm going to try to, so upside down and backwards, it would be, think about it to, okay, wow, I can't draw a star upside down. Let me try that again. I can do better. All right, so it's going to look like do. All right, there we go. So the point is that it's upside down now, and this is going to be off in this direction. There. Okay. And so this point here is, I'm going to call this XFI, YFI, negative F in the camera frame. So the Z direction is clearly the looking direction of the camera. And so by the time a photon lands on the focal plane, it's going to be negative F in the Z direction, and then at some coordinates X, F, and YF, where the I subscript is just because this is the ith star, right? Or the ith point. So its actual world coordinates is going to be XI, YI, ZI, where it may or may not be clear by my handwriting, but those are meant to be capital letters. Right? It's going to look more clear in a minute. And then finally, this point right here is going to be little xi, little yi, and 1. It's going to start to make a little bit more sense in a minute. But there's our image of the pinhole camera model. So we've got the x, y, and z directions. We've got the u and v directions, image plane. We've got a star. Hopefully it makes sense that this is this point here, the xf, yf, and negative f, the focal point, the point on the image plane, and the star in real life are all along a perfectly straight line, despite my art abilities. So we've introduced a couple of things here. So let's put this in plain English. So first, we introduce the camera frame, where x is to the right, y is down, and z is forward, or what we're going to call the camera boresight direction. So it's dead ahead is Z. Now we also introduced, I'm going to be careful about my scrolling here. Hopefully that's still enough room in case anybody's still catching up on drawing the image. We introduce the fictitious image plane, which is at unity distance, so a distance of 1, along the Z direction. Okay. It's going to make more and more sense why we did that. I want to be clear that the image plane is not real. The focal plane is real. That's where the pixels literally are in your camera, right? There actually are elements which receive photons and produce voltages or produce charge, electric charge, and those become the pixels in your image. That's literally where they physically are. At the image plane, if you break open a camera, there's nothing there, right? This is a fictitious plane that we're going to use for the purpose of image processing. Because in the image plane, the image is right side up, so it's not upside down and backwards. Your image plane coordinates, and this may or may not be clear, but actually we're going to write an equation in a second. Your real world coordinates and your image plane coordinates are similar vectors, right? They have different scaling on them. We're going to see that in a second. That's another reason why we like to use this. And finally, it allows us to work in what are called focal length normalized coordinates. So let me just write that all down. So the image plane is where the image is right side up. And we work in what are called focal length normalized coordinates. Okay, so what do I mean by that? You can imagine some point on the image plane. It is one distance away from your focal length. And so then it's one distance away from your focal point. You're taking the point on the focal plane and normalizing it by the focal length and swapping the signs, right? That's essentially what we're doing. So that you don't need to know the actual focal length of the camera to work in focal length normalized coordinates. You're basically working in multiples of the focal length. That's the idea that we're trying to get across here. So going back to a point that I was making a second ago, if you've got a point in 3D space, which looks like xi, yi, zi, and this is in 3D space, and you've got another point which looks like x, fi, y, fi, and then negative focal length, and then you take another point which is xi, yi, and 1. So this is on our focal plane, and this is on our image plane. These are not the same vector, but they are proportional. These are proportional vectors, meaning that it's the same vector, just scaled differently. And actually, the way I like to write this out is that little xi, if we're working in image plane coordinates, which we're going to be working on a lot, well, that's just big xi divided by big zi. And little yi is big yi divided by big zi, which may be obvious if you just look at the vectors, right? They're not the same vector, but they're the same direction, and we're just playing around with the scaling. We're playing around with the magnitude, essentially. So we can go from a point in 3D space, big X, big Y, big Z, to a point on the image plane, and then, well, we're part of the way there. So that allows us to go from 3D space to the image plane. I want to know what pixel that particular star is going to land on, right? And so that's my question. So I'm going to pause for questions here. Is everybody feeling okay so far? Okay. So the question is, how do we go from a point on the image plane to a pixel in an image. Wow, all right. That's my brain trying to combine the words and an image. Okay, there we are. How do we do that? So we're going to define another coordinate frame, and actually I snuck it into the diagram up there, the UV coordinate frame, which I'm just going to call the image frame. So we've got the camera frame, next is the image frame, or sometimes you'll hear this called the pixel frame. So the image frame is centered at the middle of the top left image pixel. Okay. And we have U is to the right and V is down. Okay. So if we look, the U direction kind of looks like the X direction, except we've moved the center and there's going to be some scaling, right? Because the location on the image, which is measured either in millimeters or it's measured in focal lengths, well, we want to measure it in pixels. So there's going to be some scaling involved. We're not there yet. Similarly, V is pointing in the same direction as Y, but it needs to be scaled and it needs to be moved. So there's going to be a frame transformation coming up that involves scaling and moving the center of the coordinate system. So let's draw a picture here, pardon me. Let's draw a picture here to make a little bit more sense of this. So we have another point here. Let's start with this. Here is a rectangle. And I'm not going to bother filling this with pixels because that's going to take all day, but let's say that here's like 4 pixels. You get the idea. The very top left pixel is the center of the coordinate system. Okay, for whatever reason, my pen is just wigging out here. Come on. There we go. Where this is the U direction. And this is the V direction. So ultimately, in UV pixel land, we're just counting pixels. It's 10 pixels over, 5 pixels down. That's the idea. You've also got a point right here, which I'm going to explain in a minute, called UPVP. Okay, so what do I mean by that? That is something called the principal point. The principal point, which is UPVP, is what? It's the intersection of the camera z-axis with the image plane. Okay, so what does that mean? It's not the center of the image. That's probably the first thing your brain is going for. Because if we scroll up, and don't worry, I'm coming back. We scroll up here, we are looking out the camera. The Z direction is the dead ahead direction. It's the center of your field of view, right? It's the center of your image. It's the center of the focusing that is happening because of your refractive lens assembly. Z is the middle. It is the center. Why is it not then the dead center of the image? Well, that would assume that your camera was made perfectly. And you might be saying, well, why do we care about that? It's got to be pretty close. It's like, well, close only counts in horseshoes and hand grenades. We want to get this right, right? We actually care about how much our center, our what looks like the forwards direction, is in practice actually going to be a few pixels or even more than a few pixels off from the center of the image. And that matters. We do care about that. In a pinch, if you don't have any better guess, you can use the center of the image as your principal point. But when we're properly calibrating a camera before we send it to space, we like to make sure that we do that right. So the principal point is the bore sight direction in the image, which is not the center of the image, but it is close. If it's not close, then your camera is seriously wrong. Something has gone wrong, but it's not exactly the same thing. So I want to hammer that point home. And actually, yes, I'm looking at my notes. That was the next point that I made. It is close to the image center, but not never actually at the image center in real life. Okay. So we've talked a little bit about the translation. So you can imagine that to get from the focal point to the center of this image plane, we go forwards one, and then to the left negative UP, and then up negative VP, something like that. Like we're getting an idea of translation. But what about scaling, right? There's going to be some scaling that comes up next. Bear with me. So let's talk about how wide the pixels are in real life. So the distance from pixel center to pixel center is called pixel pitch. Right? You could think of it as the pixel width or the pixel height, essentially. And so we're going to write this as mu x or mu y because they don't need to be the same thing. They can be different. In x and y directions. But pixels are usually approximately square. So if your pixel pitch in the x direction and your pixel pitch in the y direction are not extremely similar, something is probably going wrong. The thing is, when the time comes to calibrate a camera, and I wish we had time to talk about camera calibration, but we don't in this class. That might have been one of our guest lectures, but I was not able to put that together. But if you want to talk about camera calibration, I can all day. It's one of the things I like to talk about. When calibrating a camera, we don't know focal length. You actually never find the focal length through standard camera calibration techniques. You can tell me what it was machined to be, but you'll never find what it really is. You also don't know pixel pitch. You'll never find that either. I mean, you can tell me what it was machined to be, but actually it's going to be slightly different for every single pixel, right? So on and so forth. But we can estimate, there's that estimate again, the ratio of the two. And you might think, gosh, how is that useful? It's actually extremely useful. So I'm going to introduce something called dx, which is your focal length divided by your pixel pitch in the x direction. And then you're never going to guess, dy is your focal length divided by your pixel pitch in the y direction. And this can be thought of as focal length in units of pixels. Okay. Now this is fantastic. It might not be obvious why yet. So when we calibrate a camera, you don't know the focal length of the camera. You don't know, let's say it's a 30 millimeter camera. It's like, it's never really 30 millimeters. That's what they said it was. That's what they machined it to be. But for our purposes, we actually have to be extremely accurate with a star tracker. So what is its focal length really? Like, we don't know. How wide are all its pixels? They can tell you what they tried to make them at the factory, but again, it won't be perfect. And we don't even know either of those two things. What we do know is how many pixels the focal point is away from the image plane. So we're essentially saying, what is the focal length in pixels, right? What is the distance from the focal point to the image plane in pixels? And that gives us essentially what we need to know. And that is our scaling, which is going to help us in just a moment here. So the relationship, if you'll permit me to write an equation here, the relationship between the image plane point and the pixel point, we have all we need at this point. relationship between an image plane point and a pixel is, drum roll please, we have a set of equations here. U sub I, which is your width in the image, is some scaling dx times xi plus alpha yi, I'm going to make sense of that in a minute, plus up. And your height in the image is dy times yi plus vp. Okay, so essentially you could think of it this way, is this first term accomplishes scaling. This second term accomplishes shear. And the third term accomplishes shift. And I did not mean to make all three of those S words, but alliteration has been achieved. So you have a scaling, a shear, and a shift. The purpose behind the shear, and we're not going to go into a ton of detail on this, but in case you're curious, real images are never going to be perfectly rectangles. They're going to be a little bit of parallelograms, right? And so the alpha term there is to help us understand that our real camera is going to be set up in such a way that it is a little bit not perfectly orthogonal, and we're going to model that. The alpha term is kind of optional. It's usually going to be close to 0. And if you are putting together a first guess of a set of camera parameters, which we're heading in that direction, not to spoil it for you, you can essentially treat alpha as being approximately 0 in most practical cases. So we're going to take these equations and put them in homogeneous coordinates. So we can write these equations. Equations in homogeneous coordinates. And that's going to look like this. UIVI1 is equal to a matrix which looks like dx alpha up 0 dy vp 0 0 1 being multiplied by our image plane. There we go. So this matrix, we're going to define this as K, or camera, and that is the camera calibration matrix. So if you know these numbers, your camera is said to be calibrated. Okay, well, why? So let's pause for a moment because we just said a lot of things. And I want to make sure this all makes sense. The camera can be thought of as a device which takes directions in 3D space and turns them into pixel values. So we need to know the geometric relationship, the math behind going from big X, big Y, big Z to UI, VI, to pixel coordinates. That's the idea. And that math is essentially this equation. Oh, I say that, and then that's the exact moment that OneNote freezes up on me. Oh, I'm sorry, no, OneNote didn't freeze up on me. My computer mouse froze up on me. Okay, that's fine. We can go without it for a little bit, but not very long. Matter of fact, I might call a brief recess so I can go get my mouse a new battery. But in the meantime, this is the equation which describes the relationship between reality on your image plane, which is just a scaled vector of the 3D vector in real life, and then your pixels in the image. So these elements of the K matrix can be thought of as coefficients in equations or parameters in equations. We need to know those parameters to predict what pixel the star is going to lie on, or in practice, it's the other way around. We start with a pixel. What was the direction that that star was in 3D space? That's what we're going to be building towards. So I'm going to pause there unless there's any questions. That is not a great natural stopping point, but my mouse just ran out of battery. I need to plug it in. So any quick questions? Otherwise, we'll break for 5 minutes and we'll come back at maybe 7:15, 7:16. All right, good stuff. I'll see y'all in a minute. All right, I think we'll start back up again in a minute. So, um, I'm looking at how many notes I've got. We are about halfway through my notes for today, and we've been talking for an hour, and I feel like it would be unreasonable to keep you for an additional hour. But at the same time, we've got to get this material across in the next 4 lectures. So I think a good kind of happy medium is I'm going to go a little bit longer than usual today, try to get about 3/4 of the way through my notes today. And then next class, I actually have less notes than usual. Like it's going to be a kind of a shorter lecture than usual. I'm going to just have the last topic of discussion today. I'm going to push it to next class, and we'll finish up our lecture 18 notes then. And that'll be how we do it. So it's not optimal. Of course, if any of you have a schedule conflict, I know it's basically 7:20 now. So if you have a schedule conflict and you need to leave, or if you're exhausted or you're hungry, you're under no obligation to stay. You're dismissed. I'm going to keep going until we get to a good natural stopping point for today. And if y'all want to just watch the video on LMS on your own time, that's totally fine. But we are going to keep this train rolling here, and we're going to talk about. I want to get to the point where maybe not today, but certainly by partway through next lecture, it will be clear how to go from a pixel in an image to a direction in 3D space. Like that's kind of the goal. That's basically where we were all the way up here. An image pixel to a direction in 3D space. So we've kind of talked about how to go from a direction in 3D space to a pixel in an image. I mean, that's ultimately what this equation is. But there's a little bit more to it. So first, I want to be clear where the matrix K is called the camera calibration matrix, which is sometimes also referred to as the intrinsic matrix. And dx, dy, alpha, up, and vp are what are called intrinsic parameters, as in they are intrinsic to the camera. Now, there are 3 types of parameters. There's intrinsic parameters. There are also extrinsic parameters you might have heard about. Those of you that have taken robotics or computer vision or image processing, you might have learned about extrinsic parameters. I don't like to use the word extrinsic parameter. It's kind of a pet peeve of mine because parameter implies to me that it's something about the camera, right? But your extrinsic parameters is the position and attitude of your camera. That's not really about the camera. That's I like to use the word pose instead of extrinsic parameters, right? Pose is your positioning, your attitude. They aren't really parameters if they're as easy as you just change the elevation angle on your camera tripod. That's not a parameter, in my opinion. That's just how I feel about this. So if you're reading about this, you'll hear them described as extrinsic parameters. I just don't like to use that word. And then there's also distortion parameters, which we will talk about as well. Because a real camera does not follow pinhole projection. And so we're going to talk about an additional mathematical model that's going to live on top of this mathematical model, which allows us to handle the fact that our camera is not a perfect pinhole camera and actually has some radial and tangential distortion effects, which we're going to talk about shortly. So a camera whose intrinsic and distortion parameters are known is said to be calibrated. So there's a whole concept of camera calibration, which is trying to find these numbers. And actually, yeah, I'm going to skip around a little bit in my notes here. Excuse me for 1 second while I leave a note to my future self. I want this concept to come after this concept. I'm going to talk about what camera calibration is. We're just going to give it one line, but this easily deserves its own entire lecture. We just don't have time for it. Camera calibration can be performed and is performed on the ground before launch. Or in flight. And this involves capturing images whose pixel points, or say where pixel points and corresponding world points are known and understood, leaving camera parameters as the only unknowns to solve for. By the way, those of you that are interested, camera calibration would be a fantastic term project to look into. If you want to learn a little bit more about camera calibration, go find a paper on it. The idea is if we know, okay, here are, I don't know, 30 points in the image, and I actually know where all those points are in real life because I did this in some lab where I used checkerboard or some other instrument. We could say, okay, I can definitely isolate these points in the image, and I actually know where they are in real life. The only unknown is this matrix K, and so you can essentially take this equation, and there's a little bit more to it, but you rework the equation where the only unknown is your parameters, right? It kind of, you might remember like in algebra, you learn that these 3 points are all on a line, tell me, and you know that the line is y equals mx plus b. You could think of m and b as your line parameters, and if you have several points, you can solve for the line parameters. Or if you know the line parameters and you know x, you can find y, or if you know y, you can find x. So there's 3 ways to do it, right? You either know the image points, and we use k to find the world points, or you know the world points and you use k to find the image points, or you know the image points and the world points and the only unknown is k. That third case is camera calibration. So I wanted to get that idea across. There's a lot more to it than that, but I feel like that is a good first pass. Now, in practice, we often want to convert from pixel coordinates to a camera frame unit vector. That's kind of what we're after today. And so what is the inverse of this? Well, you could say, look, I know u and v and 1. I'm just going to multiply it by k inverse and get x, y, and 1. And that is basically what we're going to do. This matrix actually has an analytical inverse, in case you're curious, and that's what we're going to be talking about now. So what is this? xi, yi, and 1 is just k inverse ui vi 1. But k inverse has a structure, in case you want to type it out. If you're feeling lazy, you can just type in k, like the elements of k in MATLAB or Python, and then just use the matrix inverse function. Or if you're trying to save operations, because matrix inversions are computationally intensive, it's 1 over dx negative alpha over dx dy. Vp alpha minus up dy all over dx dy. 0, 1 over dy, negative vp over dy, 0, 0, 1. And that is the analytical inverse of your camera calibration matrix. UI, VI, 1. So start here, multiply by K inverse, and then from here we normalize to get your line of sight unit vector. Okay. So that's enough that you can actually start taking a crack at homework 1, because the very first thing you're going to need to do is find the stars in the image. Okay, well, that we will talk about how to find the stars, but let's assume that you know the coordinates of the stars in the image. Well, you can actually work backwards to find the star line of sight directions in the camera frame. Right, so that's going to be essentially the essence of the first part of your homework. Now we're going to talk about image noise and aberration effects, and then we'll stop for the day and we'll move on and we'll talk about the other stuff next class. But we're getting close to the point where we can start to tackle homework 1, which is good. Questions on this so far? This pinhole camera model, forwards and backwards? All right, cool stuff. So next we're going to talk about image noise, because images are not perfect. So the effect of noise as opposed to aberration, which we're going to talk about next. Noise changes a pixel's value. Aberration changes a pixel's location. That's the difference. So noise is you could think of it, and not exactly, as a random number that's applied as an addition or a bias to each pixel's value. That's the idea. So we're going to be making some modification to every single pixel in the image, and that is caused by semi-random events which conspire to essentially mean that the image is never truly completely black. Even when you're taking a picture of empty space, there's always going to be some value at all the pixels in the image. So the effect of noise is to perturb a pixel's digital value. So we have several different types of noise that we're going to talk about. The first of these is readout noise, which might sound a little bit familiar if we were just talking about IMUs last class. So readout noise is generated from converting electric charge or electric charges to digital numbers. And so an example of readout noise is analog digital conversion noise. Which is the result of quantizing or quantization of a continuous signal. So quick example, let's say, for the sake of the argument, that a given pixel's value is exactly 5/8, right? Exactly 5/8, which is an S rational number. Well, that's 0.625. The thing is, if we're trying to represent this as a number between 0 and 255, the best we could do is 159, which is pretty close to 5/8. This would be 0.623 0.35. And that is as close as we can get to 5/8 with a bit depth of 8. If you have a camera where every pixel is allotted 1 byte of memory or 1 byte of storage to, encode its value, then the best we're ever going to get is 159 out of 255, which is in this case what, 0.0015 of pixel noise, which is not so bad, but that is a effective noise. Like that, we have to take that into account. So that's analog digital conversion noise. There's also something called dark current. So to give you an idea here, even an image with the lens cap on isn't completely black. If you actually zoom in on the individual pixels in the image, they're never going to be 0. They're going to be some small number, but it's never going to be completely black due to various effects. So thermal effects, anything else that's going on with the camera, it's called dark current, right? So the way that we fix this is we capture what's called a dark frame. And dark frames are useful for other effects too, such as predictable stray light or fixed pattern noise. We'll talk about those. But essentially, if you take an image with that lens cap on and then just save it, and remember that that is the dark frame image, you can subtract each pixel value of the dark frame from each pixel value of your future images. And that is a pretty reliable way to remove a substantial amount of noise from your image. And this is something that we absolutely do in practice when we're working on image processing, starfield image processing for navigation. So capture a dark frame and remove from future images. The image file name that you're going to be looking at for homework 4 has DFS in the file name, and that means it's already been dark frame subtracted. Somebody's already done that math for you. There's also photon shot noise. Okay, so photon shot noise is noise associated with generation and collection of photoelectrons at the focal plane array. So that can be a messy process. It's not always going to be perfect. There's pattern noise, which can then be separated into fixed pattern noise and variable pattern noise. But this is caused by idiosyncrasies in detector sensitivity. So some pixels are just going to be more sensitive than others because that's just how they are. So it's caused by idiosyncrasies. There's no H in the word idiosyncrasies. I had to learn that. I had to look that up. In the detector sensitivity. There is reset noise. We're almost done, I promise. Because it is impossible in practice to purge all charge from the focal plane array. Between images. And then we have radiation effects. So these can cause stuck pixels, which are either full on or full off forever, bit flips, etc., etc. If you look at live feeds of cameras from the International Space Station, first of all, they look gorgeous when you're taking pictures of the Earth from the International Space Station. But if you look at images of space from the International Space Station, it almost looks like the light show that you get when you close and rub your eyes. There's like weird colors that are just basically burned into the camera. And they were burned into the camera because of radiation. Radiation kind of wreaks havoc on cameras in space. So these are the effects of noise, and I'm telling you these for academic purposes because in homework 4 you won't need to do anything about noise. The dark frame has already been subtracted from your image, but I want you to be aware of these in case you have a discussion with somebody about star trackers. Image noise is something that we need to think about. Something that you will need to take into account is optical aberration. So questions on noise or anything else so far? Okay, so we're going to have a discussion on optical aberration, and then we're going to stop for the day. And I appreciate y'all sticking around with me. So there are 5 basic types of aberration. You can think of aberration as actually messing with the image, right? We're not talking about messing with the pixels, which is kind of a electronics, electrical engineering, and physics type problem. This is more of an optics problem where we're somehow blurring or smearing or distorting the image because of, well, because of these things. So there's 5 of them. They are spherical aberration. These are the 5 classical sources of aberration. Spherical aberration, chromatic aberration, astigmatism. I have that in my eyes. Curvature of field, and lens distortion. Let's talk about what each of these does really briefly here. So the first one, spherical aberration, has what effect? It essentially blurs point sources of light. Chromatic aberration or coma, it points of light, we'll say this, point sources of light that are near the image edge blur into a crescent shape. So if you imagine that a star is supposed to be kind of a roughly uniform blob, around the edge of the image, you'll get kind of this shape. It'll be all like kidney bean shape, essentially. That's caused by coma, which is an effect of the lenses. All of these are effects of the lenses not being perfect, essentially. The next is astigmatism. And so this is where the blur is greater along one axis than another. Okay. Curvature of field essentially means, you can think of it this way, you've got a series of refractive lenses which are generally parts of a sphere, essentially. You could think of each lens, convex or concave lens is part of a spherical surface, and those will not project light onto a flat rectangular surface. That's not how it works. So what's going to happen is it is impossible in practice for entire image to be in focus at the same time. That's the idea. There will always be some blur around the edges if the middle is sharp, or if the edges are sharp, the middle will have some blur because you can't project light using these spherical lenses onto a flat focal plane array. Now, you can, but you're going to have to pay for it because of this effective curvature of field. And then the big one, and this is what really bothers us as navigation engineers, is lens distortion. This one is the important one. So we're going to put a little star next to it. Lens distortion. Okay, why do we dislike this one so much? The other ones essentially are various sources of blur, but this one actually moves stars in an image. If you have a star field image, you now can't trust where the stars are, which the whole point of this lecture is trying to find the line of sight directions to stars, but they are moved by the effect of lens distortion. So that won't stand. We need to do some mathematical modeling for lens distortion. There's two types that we're going to be talking about in this class. The first is radial distortion, and the second is tangential distortion. And so these actually move points in an image, which is completely unacceptable. So we must account for this. So I'm going to draw y'all a picture. I'm going to teach you some equations on how to account for this, and then we're going to wrap up for the day. So this is where my artistic skills are going to be stressed to their absolute limits here. So imagine this is our diagram for radial distortion. Okay, so imagine that we're starting with a nice rectangular image that looks like this. And you've got lines here and here. And just imagine these are all perfect squares. If you had radial distortion, I'm going to make a dotted line, like this was the original square. And then here. There we go. If you had something called barrel distortion, which is where each point was kind of like sucked into the center of the image, then this same shape would look a little bit like this. It's still going to be perfectly straight lines in the middle, but around the edges, it'll look like that. That's the best I could manage. Pincushion is the opposite. Pincushion is when points are pushed away from the center of the image. And so that will start to look like this. Right? Where again, along the main two axes, it looks about the same, but you start to get this effect going on. So we've got barrel and pincushion. Two different types of distortion, but really it's the same type of distortion where one of them is the opposite of the other, right? Just the same way that negative numbers are just positive numbers in the other direction. Same concept. So these are radial distortion effects, and we're going to talk about how to model those. Now there's also tangential distortion effects. So imagine that you take an image that is supposed to look like this. It's supposed to be a nice square with some supporting grid lines. That's my best square. There we go. And then I'll put in the ghost of the original square here so you can see what I'm talking about. And here. Close enough. So in the one case, we would have something like this. These are, of course, severely exaggerated. Okay. This is tangential distortion. Or something like this. There we go. Something like that. Right. So these are barrel pincushion distortion. This is tangential distortion. So your barrel distortion is caused by, or sorry, your radial distortion is caused by the lens itself tending to either create a fisheye or like an anti-fisheye effect. And then your tangential distortion is caused by your focal plane array not being perfectly perpendicular to the camera bore sight. So you can imagine that you, like, you know, your teacher in school has a projector and they're trying to project the projector onto the whiteboard and they don't have it lined up quite right. So one side of the image, the projected image, is clearly smaller than the other. That's basically what this effect is. So your misalignment causes your tangential distortion, and then the actual physics of your optics causes your radial distortion. But all of it moves stars in your image, and that's completely unacceptable. So we're going to introduce 5 more camera parameters. They are K1, K2, K3, P1, and P2, which we're going to use to mathematically model these effects that are going on. So, to account for radial and tangential distortion, we will use the Brown distortion model. That's supposed to be the letter D. And this is sometimes referred to as the Brown-Conradi model. Sometimes people include the second name, sometimes not. So here's the idea. If R is the distance that your pixel point is away from the center of the image, so R squared is xi squared plus yi squared, right? It's Pythagorean theorem. R is the distance away of your point from the center of the image. Then here's your distortion. Xi prime, yi prime. So this is your distorted point. This is what we actually see, is some function of your original point, which looks like this. Xi times some polynomial, 1 plus k1 ri squared plus k2 ri to the 4th plus k3 ri to the 6th. And then this is yi times the same polynomial, k1 ri squared, k2 ri to the 4th, k3 ri to the 6th. So that is our radial distortion term. Plus, here comes our tangential distortion term, 2p1 xi yi plus p2 ri squared plus 2xi squared. And then on the bottom, it's 2p2 xi yi plus p1 ri squared plus 2yi squared. And this feels like a lot. This feels like a lot, but here's essentially what we're getting at. This is the distortion point. This is what we really see. This is the original point. This is what the pinhole camera model would predict. So this is the pinhole point. And then all of this is what accounts for radial distortion. And all of this is what accounts for tangential distortion. There we are. And so, like we've said before, all models are wrong, but some models are useful. This model allows us to use 5 numbers to predict the movement of stars in an image that are caused by misalignment and the spherical effect of lenses, radial and tangential distortion, that is. Now, we're almost done, because you might be saying, well, probably you're saying, Paul, I'm tired, I want to stop. I know, we're almost done. But you're probably saying to yourself, well, Paul, isn't the whole point of this lecture, if we scroll all the way up to the top, and boy, we've done a lot of stuff, we're trying to take an image of stars and determine the apparent line of sight directions to each of those stars. Okay, so we know that the pinhole camera model uses essentially this equation to map between points on the image plane and then points and the pixel points. And we know that we can work that backwards. We can start with the pixel points and find these image points, which are the image points that are predicted by the pinhole camera model. Then the question is, all right, well, now you just taught us all about optical aberration and distortion. Don't we need to undistort things? Like you've shown me how to go from the perfect point to the real point, but we start with a real point. We need to go to the perfect point, and that's absolutely correct. And you will need to undistort points in homework 4. So that's the last thing we're going to talk about. This will take about 5 minutes. So what if we're starting, it's supposed to be an apostrophe, with an image, and we're trying to undistort points? Well, what we would do, this equation has no inverse. So we're going to need some iterative solution. There is no closed form solution. A little bit like how there's no closed form solution to Kepler's equation, right? All the way back in the beginning of this class. There's no closed form solution. So we will guess and iterate. And that looks like this. Xi initial is the distorted point, which is where we're starting. Yi initial is also the distorted point. And then remember that Ri is just xi squared plus yi squared. So our new xi is xi prime minus 2p1 xi yi plus p2 parentheses ri squared plus 2xi squared, close, close, everything divided by 1 plus k1 ri squared plus k2 ri to the 4th plus k3 ri to the 6th. And similarly, we've got an equation where our new yi is yi prime minus 2p2 xi yi plus p1 ri squared plus 2yi squared, close, close, all over the same denominator. 1 plus k1 ri squared plus k2 ri to the 4th plus k3 ri to the 6th. And so you would do all of this. We would iterate until xi and yi converge, which in practice, this is usually less than 5 iterations. So what I did when I wrote my Star Tracker code was I start with well, first we haven't talked about star centroiding yet, so that's actually going to come up in the next lecture, but we need to be able to take star field image and find the center of each star, which is not trivial. Once you have the center of each star, that is going to be a coordinate in pixel space, right? That's a UV. So we go from UV to xi, yi using the intrinsic parameters. But we recall that that xi, yi is actually distorted because our whole image is distorted. So then we work backwards from xi prime, yi prime to ultimately find xi and yi. And finally, when I coded this up, I just ran it for 5 iterations. I didn't even check for convergence. And then you've got xi and yi. Finally, you can stack those into a vector and then normalize it to get your unit vector in the digital image. All right, that's plenty. Y'all have put up with a lot. This has been a rough first lecture back. I've got another page and a half of notes on starfield image processing, specifically line of sight estimation, centroiding, thresholding, stuff like that. I think that we can talk about that next class. So why don't we stop? So if y'all have any questions, you're free to stick around, but y'all are like officially dismissed and we can talk about that next class. And I encourage you to get in groups and start talking to people and start thinking seriously about homework 4. There's like a lot of work to do with homework 4. If you are not feeling very social and you can't put together a team, email me because I don't want anybody soloing homework 4. I'll put you in a group if I have to, but like y'all got to work together on this one. All right. Thanks, everybody. Go on and get out of here unless you have any questions for me.